Hello everybody. In this video, we're going to talk about some background knowledge of vectors which will be related to the future learning of the multivariable calculus. And those are from section 12.2, 12.3, where we cannot go deep into the details. We only mention some basic properties and concepts which will be related to our course, especially for the section 14.5. And if you have more questions, then you can go to the textbook to this chapter 12 and find out the related informations. Alright, so we first talk about 2D vectors. Usually 2D vectors are given by two numbers, v1, v2, and the most special or important special 2D vectors are 1, 0 and 0, 1. And usually people to get some image in for 2D vectors, we can map those 2D vectors into xy plane. So suppose 1, 0, this vector is given a name I, and j stands for another vector which is 0, 1. Both are very important and fundamental for 2D vectors. So 1, 0 means we can take x coordinate as 1 and y coordinate as 0. Then the point 1, 0 is here, and we call this as I. And this is called j, which is 0, 1. And if you have any vector like v1, v2, then we can write it as v1, 0 plus 0, v2 by addition. And we can take out the constant. When we take out this from the first term, then the first term becomes v1 times 1, 0, and the second term is v2 times 0, 1. So here the first one is called I, the second one is called j. So it becomes v1i plus v2j. Now the length of norm, the length of the vector is given by Pythagorean theorem, so which is magnitude of v, or length of v, or norm of v. All those are the same concept, which is square root of sum of square root of two numbers. And the direction is a unit vector. So by direction, it is a unit vector given by normalizing the given vector v by its length. So we're going to look at one example here. V is given by 3i minus 4j, be a vector. Then find the length and find its direction. So the length is given by, we denote it by v with bar, which is square root of sum of two numbers. Before doing that, I want to rewrite v as 3i minus 4j, but I can rewrite this into standard form of 2D vector because j is 0, 1. And then if you put them together, then this is 3, 0, and plus this is 0, negative 4. So 3, negative 4. We can think of this geometrically in the xy plane. So 3 is x coordinate, y coordinate is -4, so v is here, and the magnitude of v is indeed the length from origin to this vector, and which is given by the formula 3 squared plus -4 squared, and then take the square root, which is 5. And this can be seen from this Pythagorean theorem using this right triangle. Alright, what is direction? Direction is a unit vector which is normalizing v in the same into the unit length, or length 1. So let's say u is its direction, then it's written by v over its length, which is v is given by 3i minus 4j, and its length is 5. If you want, you can write this as 3 over 5i minus 4 over 5j. Or you can directly write this as 3 over 5 as the x coordinate, -4 over 5 as second coordinate. Those are all the same. Alright, dot product. So given two vectors, you cannot just randomly multiply two vectors. There's a product rule which is called dot product, which is denoted by v dot w, and this is exactly the sum of products of corresponding coordinates. So if we look at, and this also follows this cosine law. So let's first look at what v look like. V is v1, v2. From here, v1i means v1 is x coordinate, v2j means v2 is y coordinate, and w is again w1, w2. And what is its product, dot product? Then you just do the multiplication of corresponding v1 and w1, and which gives a number. So number times number is clear, plus we do v2 times w2, so component wise product, and then add them together. And this actually gives you another formula, which is cosine product of the length times cosine theta, where theta is their angles. So suppose you have v here and w here, and theta is here. Theta is the angle formed by these two vectors. Alright, now the cosine formula is very important, and this actually tells you an information about perpendicular. So what is perpendicular? V perpendicular to W if the angle is 90 degrees. That's the definition. But using this cosine formula, we can actually have further information or easier criteria to identify if two given vectors are perpendicular or not. So we see that from the cosine formula, v times w, or v dot w, is v length and w length and cosine theta. So if theta is 90 degree, or in radian we can write this as pi over 2, then v w and cosine pi over 2, and this guy becomes 0. Cosine 90 degrees becomes 0. So 0 times anything becomes 0. So that gives us the next useful property. V is perpendicular to W, or forms 90 degree with W, if and only if their dot product equals 0. So let's look at another example. So V is given by this with, there's a typo. So U is given by 3i plus 4z, and V is given by negative 4i plus 3j. Are they perpendicular to each other? Then we want to look at if U I'm sorry, it looked like we should have different notation. So V and W, this is W. So to justify they are perpendicular, we should look at their dot product. If this dot product becomes 0, then you can say yes. If not, then you can say no. So this is 3, 4, which is V, and W is negative 4, 3. And then these two gives negative 12, and these two becomes positive 12, which is 0. So yes, they're perpendicular. Determinant. For 2 by 2, determinant is a number for a given matrix, 2 by 2 matrix. We can also define determinant for m by m matrix. So first of all, what is matrix? 2 by 2 matrix is given by 4 numbers arranged in 2 by 2 box. So each row have 2 numbers, each column have 2 numbers. So it could be A, B, C, D. So this is a matrix of 2 by 2 shape. And the determinant of this 2 by 2 matrix is given by A times D minus B times C. Some people say cross product, but this is not cross product. It's just informal way. But determinant A is defined as AD minus BC, which is a number. Could be a negative number. We can look at, and determinant of, now let's look at determinant of 3 by 3 matrix, how to generalize from 2 by 2 matrix. So determinant of A, this is a little bit complicated. So what we do is we first need to know what minor means. So Aij is the determinant of the sub-matrix by deleting ith row and jth column. So we see that A11, what is A11? A11 is the minor corresponding to A11, small A11, this component. In other words, if you are deleting A11 row and A11 column, then the remaining box is given by A22, A23, and A32, A33, and its determinant, it's a number, which is A11. Now, what is A12? A12 is going to be, so I'm going to delete A12 row and A12 column. Then the rest of 4 numbers for A12 is going to be given by A21, A23, A31, A32. And now we look at A13. I'm not going to actually delete it from A. You can just imagine what we will have in this small box, 2 item matrix. So we can delete A13 row, in other words this row, and delete A13 column, then the remaining 4 numbers are given by these 4. So determinant of A21 A22, A32, A33. I'm sorry, this is not A31. So A21, A23, and A31 and A33. And by this formula, determinant A is, this is called first row co-expansion. So the determinant can be computed in many ways, but this is the basic, or you can think of this as the definition of determinant of 3 by 3 matrix, but it could be defined in equivalent in different ways. But this is called co-expansion formula by first row. So what it means is, when you look at when we expand this by expansion formula, co-expansion formula, what we can screen down along the first row, and we can put plus sign, minus sign, plus sign. And then if you have plus sign for A11, then you can just write plus A11. And A12, you can put negative sign. A13, you can put positive sign, right? And right after A11, you won't put its minor. A12, you put its minor. A13, you put its minor. And this is the formula to compute determinant of A when A is given by 3 by 3 matrix. All right, here's one example. So we go for, so we're going to use first row expansion to find determinant of A. So determinant of A is going to be, first I put flip signs along this row, and then that means plus 1, minus 0, and plus 0. So I labeled, or I put first rows in my expansion, and for the maybe I need a little bit more room for this. And then it's minor. What is minor? Determinant of the rest of them. The minor for this one is going to be given by 2003. And yes, I don't need that much room here. And 0 times its minor is determinant of 4 numbers. So when you have 0 coming from here, then you delete this row and this column. So that is 1003, 1003. And when I have plus 0 here, then its minor comes from this one. So determinant of 1200. But we know that at first we noticed that 0 times anything is 0. 0 times anything is 0. So we don't actually need to take care of these two computations, determinants. The only thing gives non-zero is 1 times this determinant of this. So 1 times anything is 1, and this determinant is by 2 times 3, main diagonal, minus off diagonal, 0, 0. So 2 times 3 minus 0 times 0, which is 6. All right, and here's another remark. So the determinant of a triangular matrix is the product of diagonal entries. What it means is, by triangular matrix, we mean something like this. So if you have 3 by 3 matrix, everything, suppose the matrix has 0 values for every entries below the diagonal entries. By diagonal we mean this. So if you have entirely 0 entries below the diagonal and above the diagonal could be anything, then this is called upper triangular matrix. Upper triangular matrix. And if we have non-zeros below diagonal and zeros above the diagonal, then this is a lower triangular matrix. And the determinant of triangular matrix could be upper or lower triangular matrix. You don't have to follow this coexpansion formula. Only thing you need to do is multiply these three numbers in the diagonal lines. So we can verify that. So for A, this is, we find this is lower triangular because upper half gives zeros. Then we can if we know this trick, then you can immediately multiply 1 times 2 times 3, which is 6. All right, we're going to stop here.